Hello, good afternoon to all of you, and good morning if you're in other parts of the world. I'll just be waiting another couple of minutes for some other attendees to arrive, and then we'll make a start on the webinar. Okay, then. So it's 3 o'clock here in the UK. We'll make a start on the webinar, which is an introduction to TruForm SW, adding SolidWorks optimization into your process. So welcome to all of you. My name is Martin Gambling. I'm working here at GRM Consulting, where we're specializing in optimization software, products and services. And through this webinar, I'll be introducing you to TruForm SW. So I'll start off by giving you a brief introduction to GRM itself as a company, before talking about topology optimization, which is the process that's embedded inside SolidWorks with TruForm, a little bit about its benefits and how it works, and then an overview of the additional suite of tools available at GRM for both topology and further extended optimization methods. I'll then talk about TruForm itself, how it works, how it's integrated into SolidWorks, and then talk a little about how and when to best apply TruForm into your design process to make the most of it, and integrate it into the current processes you're doing for structural component design. And then we'll end with a case study looking at a superbike fork end, which has been developed through TruForm for an additive manufacturing process. So who are GRM? Well, as a company, we've been established in the UK for a little over 12 years, specializing in the field of structural analysis and optimization. As a company, we've expanded over the years to now support the software development and distribution of other people's tools as well, focusing on FE analysis and optimization. So with that, we provide obviously the software itself, technical support, and then standard and bespoke training courses relating to it. On the other side of the business, we then have our engineering consultancy. We'll not go into details of that today, but just to let you all know that the other side of the business supports optimization projects, design engineering, and advanced simulation methods through FEA, CFD, and so on, including composite analysis and design and development. So on to the focus of the day, which is TruForm SW and the benefits of topology optimization. For those of you that are not so familiar with topology optimization, I'll just take you through a little bit, very simply, about how it all works. And we'll start off with what you should be able to see on screen there, which is a very simple C-shaped hook. And in terms of what optimization is and what it does for us, we can use this as an example to explain it a little clearer. So if we take this part and we fix it at our top 4 fixing holes, we can then apply a force to the lower section there. What we want to achieve here is to design the part that's as light as possible, most efficiently carrying the load through the system. So what topology optimization does for us is it develops that ideal load path, that most efficient usage of the material that we've got available. So just taking an example here, this is a typical result you'll get from a topology optimization on such a problem. So relating that onto SolidWorks, we simulate using the simulation modules of SolidWorks, and then we add the TruForm topology to it. So in terms of how topology works, I'm just going to have just a single slide on here. We're not really going to focus on the technical theories of the day too much, but just to break it down a little bit so you can understand the processes at work. First of all, we start off with a finite element analysis, or a simulation of your component that you're designing. So we have our hook on the left there. And what we're actually doing in the process of topology is we're basically cheating the system a little bit and factoring the stiffness of each of those elements, depending on whether we want to keep them or whether we don't want to keep them. And what we do, if we take just our single element you see in the center of the screen there, what we're doing with this is we're going to modify its stiffness with a factor from 0 to 1, and also its density. Now the mass of the part will vary as a nice linear trend, but the stiffness will factor from 0 to 1 with what's called a power law. What that means is material that exists that's neither here nor there, as it were. So either we have the material or we don't have the material, which allows us to form our load paths. Material is in between, so it becomes quite a low stiffness compared to the mass of that element. So that penalty method, this power law method, prevents the topology from evolving essentially halfway between some material and no material. So this process will ultimately erode our material down to create the load paths through the elements that are doing the most work in our structure. Now, in terms of the benefits of topology optimization, key thing we want to do here is understand what can we get out of it as a process in our design. So first of all, we can look to develop the optimal load paths for the structural load cases we want to consider, and that will give us the opportunity to develop right first time designs. Secondly, and probably I would say this is one of the methods that's less well used, is if you have a design that you've engineered yourself, it's not quite meeting the performance requirements you want it to. It's perhaps not quite as stiff as it needs to be, or the stresses are too high. You can very easily use TruForm and the topology process to identify the most efficient place to add extra material to resolve your design issues. And then the final application of topology is if you have an existing design and you're happy it meets all the performance requirements, but it's just a little bit heavy, there's too much material in there, so your material costs are too high, you can use topology to identify the best places to remove some of the material, giving yourself a weight saving with very little detrimental effect to the part. So before we go and look at those steps in a little bit more detail and seeing how they're applied in TruForm, we'll just give you an overview of the tools available in our suite of optimization software. So if you see the diagram on screen at the moment, you can see how TruForm fits into our suite of tools as an integrated solution, in this case inside SolidWorks, and as a topology optimization tool. So it's bringing that process to the SolidWorks user. Further to TruForm SW, we also have TruForm, which is our original TruForm product, embedded in another Dassault product, which is Simulia, or Abacus as it's often known as. And then we also have available GTAM, which is topology optimization added into the ANSYS mechanical workbench environment. And there's a new product we also have available through our partners. We have GSAM, which is an extension to ANSYS workbench, which allows us to do more than just topology optimization. There are extended structural optimization methods inside ANSYS. And for those that want to integrate dedicated solutions for optimization. We have a complete structural optimizer in Van der Platz's Genesis product, which is a full FE analysis solver and optimization tool, all embedded in one with its own dedicated pre and post environment. And then we also have, for multidisciplinary optimization, we have a product called VisualDoc, which is allowing us to wrap around optimization and develop process automation around almost any process, be it structural, thermal, CFD, dynamics, any part of the engineering process. We can add and augment it with optimization. So as an overview, you can see we have tools aimed at the different levels, so at the designer or the general optimization user, which is where we would place TruForm, allowing you to get really good benefit whilst fully integrating into your design process, right through to the simulation or the optimization engineer that would look to use the more complete tools of Genesis, VisualDoc, and GSAM. So just some further information of what's coming up. So just to let you know, TruForm at the moment, coupled with the SolidWorks own offer of buying premium for basic, you can get a discount of 25% off TruForm, which actually allows you to purchase SolidWorks Premium and TruForm for less than the standard price of SolidWorks Premium. So it's allowing you to get this capability at a good cost-effective price. And then for further information on the additional products, there's a webinar on the 10th of December overviewing GSAM, which is the ANSYS structural optimization toolset. And then we have an overview of the latest features in Genesis on the 20th of January. And you can find more information about this at our website at www.grm-consulting.co.uk. So now on to TruForm itself. So next step we'll do is to go through an overview of TruForm, its interface, and some example applications. So in terms of the interface itself, so here we are, we have SolidWorks 2016. For those of you that may or may not have adopted it yet, this is the latest and greatest interface for 2016. And we'll do our demonstrations in SolidWorks 2016 today. But please bear in mind that TruForm is available in both 2015 and also 2014 versions of SolidWorks. So the interface is an embedded add-in to SolidWorks, so it just appears across the top of your command menu. And we've got two options: one, to perform an optimization, and two, to import some results of a previous study. And then working our way through what we see on the screen, we've got our TruForm optimization setup panel. So we first start off by choosing our body that we would wish to optimize. Then choose the simulation study we want to focus the optimization on. Once those two options have been selected, TruForm will default to targeting 30% of the mass of your part, and then you can just simply choose from that any further revision that you want to define the mass of the body that you're going to optimize. Then the last step of the process to set up the optimization is to choose the optimization refinement level for your TruForm study, and the next slide explains this in a little more detail. And once that's done, you simply submit the optimization, it's exported and run, and the results will be brought back to you inside SolidWorks. So in terms of what the refinement level means, some key facts to understand about TruForm is it supports 3 levels of optimization refinement, and these are independent of the mesh data you're using inside SolidWorks simulation. And we do this for technical reasons of achieving a better topology optimization result by creating a mesh that's more suitable for the application of optimization. So to go through the 3 coarseness, 3 refinement levels, we have coarse, which would present to you a topology result in approximately 1 minute, so you can get very fast indicative results of the optimization of your part. The standard default refinement level will take between 5 and 10 minutes to develop an optimum solution for you. And then once you have done perhaps some of the early studies and you want to generate a more refined solution to ensure you're capturing all of the efficiencies of using the topology process, you can run a refined optimization, and that will take approximately 40 minutes to 1 hour to solve. And if you look at the results you see on screen there for this example, where we have simply a block with some holes, fixing points, and a load applied, you can see that fundamentally the results are the same in each case. You're just adding a little, an increased level of detail to the results of the TruForm optimization as you add refinement. In terms of bringing the results back in and developing your designs around them, you can bring in the data either as a graphics body into SolidWorks or as a solid body. Both methods are currently using a triangular facet STL based data format. So you can either manipulate that directly or use it as a guide to develop your part. So moving on to how and when to use TruForm so we can get the best benefit from it. If we go back to these three benefits of topology, you can see we can develop a design from scratch to get the right first time design load path. We can improve the performance using a process called RDM, which is the reinforcement derivation method, or we can reduce the mass and material cost of an existing design. So if we take a look at the first step, which is to develop the right first time design, I'll take you through the processes inside SolidWorks now, whereby we can create our design space and our simulation study. Then we want to perform a TruForm optimization, review the results and develop a design, and then verify that performance inside the SolidWorks simulation module. So here we are in SolidWorks 2016, and we've got a very simple test model here to demonstrate the process. So we're switching over to our simulation study with the test loading, and you can see we've got a load on the top of our pillar, and it is then supported on the bottom. So all we're going to do here is just simply run the simulation inside SolidWorks, and we'll just see the results that we get. Okay. So we've built up our simulation. So this, if you're a user of the simulation module inside SolidWorks, this is completely unchanged, and you work in the same way as you always would. The difference being here, rather than designing and assessing the part you wish to manufacture or complete the design, you develop a design space of where the material could be. So once you're happy with your simulation study, you enter the TruForm module and set up your optimization. So first of all, we're going to select the body to optimize. Then we'll choose our simulation study, and you can see we've got a target mass has been presented here in grams. For this example, we'll set it to 200 grams. Choose the coarse optimization method to give us an indicative look at the design load paths, and simply run the optimization. So you can see now the optimization has been exported and run. And once it's complete, you get the option automatically presented to you to either open the results as a graphics body or solid body, and then you can either choose in the current window or in a new solid part window. So here's our results. In this case, we brought them in as a graphics body, and you can see them as the material layout to support that vertical loading. So what we'll do next is we'll just use some reference results here to roll forward through our design tree. So first of all, we'll cut out the material that's unwanted, and then add some fillets. And then with an extra sketch, just trim and taper that rear leg, as TruForm is suggesting, and then finally add a nice smooth fillet to complete the shape. So you can see very quickly we can develop around the part to achieve what we want as a design. So just to confirm, our next step is then to perform our simulation study, and because the constraints were on one continuous surface, we just need to update our simulation study here to fix both legs. We'll hide away our STL results and perform our simulation. Now in this first example, we've got no specific targets, so we're just going to demonstrate how the part is efficiently managing the load. We'll move on to our second example where we'll have some more specific requirements to study. Okay, before we do, just to check, so we set a target of 200 grams for our part, and if you look here, we've achieved 220 with my interpretation, so a bit of refinement in my interpretation of the TruForm results, but you can see very close to the target that we wish to achieve. And before we conclude this first example, I'll just show you how else you can import the data. So in this case, we'll import the results as a solid body in a new window. And one of the benefits, particularly as well in SolidWorks 2016, for those that aren't familiar, is you're able to import STL-based body data with more facets, and it works more efficiently than previously in 2015 and 14, if those are the versions you're on. So reasons to update to 16. And you can see here, once we've got the data imported as a body, you can start to manipulate that to make further changes to it, merge it to other parts of your structure, should that be required. Okay. So we'll leave that example, and we'll move now on to our second application of TruForm. And here we're going to take a challenge of where we've got a part, we've designed it, and we're at that point where we're about to enter the loop of iterating our design to get to our desired performance. And so often here we're looking at, I'll add a rib here, or I'll thicken this piece of material. And what we're trying to do is use TruForm to guide that development process and really reduce the number of iterations and get to a better answer. So what we'll do in this example, we'll assess the current part, then we will create some additional design space and then perform a TruForm only on that particular additional space, and then we will assess the performance using the results of TruForm and then update and verify our design. So here we have, again, I think this is actually one of the first tutorials in the SolidWorks simulation module. So what we're going to do here is just take you through the performance. So as you run the model to start with, we have a baseline displacement of 1.7 millimeters. And for our case, we're going to consider that this is too much. We want to reduce that displacement. So what we want to do now is allow TruForm and ourselves some space to add additional reinforcement. So here we're just going to create a small sketch and extrude a feature into our current part. And one of the key tricks here in terms of getting the best out of TruForm is utilizing the capability of SolidWorks to choose to either merge or not merge some of your operations into the same body. So here we're going to add 25 millimeters of material where we could reinforce the component, but we're not going to merge this into our body. So that will allow us to choose only that particular part of the component in TruForm for the optimization. So our next step is just to revalidate our simulation study, and we'll do that very simply. We just need to assign a material to that additional body that we've created and then rerun the simulation to confirm the performance. Okay. So you can see here some of the other nice features of SolidWorks at this point is that through the connections module of the simulation study, it's detected automatically that this body, whilst it's a different body to the part that we started with, it's completely adjacent, and it will tie that into our simulation. And that makes the whole process much more streamlined for what we're trying to achieve here, which is to reinforce the part. So again, our next step is to enter into TruForm, and what we'll do here is select our additional material body. As you can see, that's appeared. Our load case is already selected because it's the only one in the model, and we're going to choose 200 grams of additional material, so just a small amount here, maybe only less than 10% of the current part as additional material. So just where can we reinforce? Again, we'll run a course optimization for this tutorial example. These examples that I'm demonstrating as well, they're part of the tutorial set that's available if you want to work through and have a go of TruForm SW. So now that optimization has been run, you can see we can suppress out the design space, and we're left with our small solid body of where it feels it's most appropriate to reinforce your part to maximize the stiffness and reduce that baseline displacement from 1.7 millimeters. So what we'll do now, we'll take advantage again of some of SolidWorks simulation's useful capabilities, is we will take that imported body and we're just going to edit some of the connecting modules available in our simulation and say, well, you know what, even though it's not quite touching, we're going to connect that for our simulation. And so we can quickly assess the improvement we've achieved through adding this extra part to our design. So remembering that our baseline was displacing 1.7 millimeters, what you can see here is with the updated performance, we're reduced down to 1.2 millimeters, so in fact just a little under that, with our TruForm added reinforcement. Okay, so as the final step of our process here, we will switch to our updated reference model, and in the same way as the first example, I'll just run through these design updates, which in this case are extremely simple. We'll just create a plane where we want to add our reinforcement, and then we will draw a simple sketch and extrude the additional rib exactly where TruForm is proposing it. So we just suppress out our TruForm results and validate our performance of our design in the simulation module. Okay. And so you can see on screen now, we started off with our simple bracket, which was displacing 1.7. We've reduced the displacement to 1.2, which is a 30% increase in stiffness, and we've done that with just an 8% increase in mass. So you can see it's really maximizing the efficiency of that additional material we're putting into our part. Okay. So on to our final example for the application of TruForm. We'll take an example whereby we have a part, it is meeting our stress and our stiffness requirements, but we just want to question whether we can reduce some of the mass, and we'll use TruForm to identify the most efficient places to do that. So what we'll do, we'll create a simulation study of our designed part, perform TruForm, review the results, and remove excess material, and then we'll verify our performance. Okay, so here's our part, supported in this case by four pins that are restrained, and then the load applied here at the bottom. And again, following some of the logic I explained in that previous example, what we have here is we've got separate bodies inside our part, allowing us to select which parts of the component we will let TruForm erode away and optimize, and which parts we consider to be fixed as a design. So just a note here, so we're displacing at about 0.4 millimeters of displacement. So that's an important number to note as we go ahead now and perform a TruForm optimization. So in this case, rather than defining the default low mass fraction of around about 30%, maybe even less, to develop an efficient layout, we've got quite a well-established design. So what we're going to do here is give it a lot more mass. So we're looking more about the material we're going to remove from our part. So in this case, we've set 5.5 kilograms as our mass, and that's removing approximately 20% from our current part. So in this example, we're going to run at the standard refinement level, so we'll leave that as default and simply allow that to run. So just to confirm on the times, in this case, this solve time took about 10 minutes. So typically a standard refinement is between about 5 and 10 minutes to solve the optimization. So on completion, we'll just bring in our TruForm results as STL graphics body data, and you can see that underneath the part. So we'll just simply hide the part for the moment, or hide the body that we've applied the optimization to. And you can see here it's indicating where we can remove material. So these two diagonal ribs on the main section have been removed, and we've introduced a lightning hole. And then in just a moment. Okay, so now what we'll do is we'll work our way through the various design updates to remove the material to follow the suggestions of TruForm. So we'll start off by removing the two ribs from that central section, that main load path section that we're not doing much work. Then we'll introduce a cut hole through the surface. And as the next step then, we'll trim away the loaded region and remove that excess material that is applied. Okay. And as the next step, when we start to study the TruForm results, you'll see that whilst we had two diagonal ribs in this area, only one was necessary, so we have removed one of those. And then we're just going to tidy up this upper area to remove that excess material. And then finally, if we take a look at the back surface, we can see that this material on these corners is not really required, so we've put some variable fillets on there just to trim that out. So here we have our updated part. So we'll now verify that in the simulation study. And take a look at how it's performing. And albeit a very, very small difference, we've actually managed to reduce the stress by 1 megapascal, but they're both remaining very constant at around about 220. And then if we take a look at the displacements, we have a displacement at that loaded corner of 0.404 compared to 496, and that gives us an increase in stiffness in displacement, of only 2%. So just to summarize this, you can see we've taken the part, and with very little effort at all, we've reduced the mass by 17% with no change on the stress and only a very, very small increase in displacement. So you can see here on some of your existing parts, it's very easy to get really big benefits from applying TruForm to your design components, which is going to give you a return on investment of material savings and part savings very, very quickly indeed. Okay. So just to expand a bit on these simple example parts, I'll just take you through a case study that has been performed by the Manufacturing Technology Centre here in the UK for K-Tech suspension. These are a company designing, developing and manufacturing suspension for motorbikes. And here this particular application of TruForm was in the development of the suspension fork end, so the mounting for the brake caliper. And this was a part that is to be manufactured using the additive manufacturing process, so that gives a little bit more freedom as well to what can be achieved through the topology optimization. So just to look at the part that we're optimizing, you can see here's the front wheel assembly with the calipers, the fork end, and on the right we have the exploded view that shows in the center the fork end component that we wish to optimize. So we'll just summarize how it began and where we ended up. So the original part was machined in 6082 T6 aluminium and weighed 570 grams. After the optimization through TruForm, the part has been reduced in mass to 419 grams. This is using a comparable aluminium in the additive manufacturing process with very similar material properties. And when you consider there's two forks on the front wheel of the bike, that gives a total saving of 302 grams, which is certainly quite a significant saving. So in terms of how this has been developed and optimized, we've taken the worst case loading, quite an abuse load case of the motorbike being braked hard with the back wheel off the ground, and then the front wheel dropping into a pothole, inducing a 3G pothole braking load case. So here we've got loads applied to the wheel axle and obviously the braking torque applied via the brake caliper. So taking a look at how we've considered that in SolidWorks through the simulation module and then preparing it for TruForm, we've designed here, as you can see, a fairly blocky design space for the brake caliper component, and we've put non-designable regions, so separate bodies in our solid part for where the axle fixes, the threaded insert for the bike fork, and then the caliper mounts themselves. And we've applied the load of the brake calipers via this generic representation just to put the force into the fixings. We've fixed the bike fork end and applied also the axle load to the bike axle. So as you've seen how easy the process is to apply TruForm to your simulation model inside your SolidWorks part, we've done exactly the same process here, and we've achieved the results that you see on screen. So this is our developed result from TruForm for the bike fork end, and so our next step in the process is to remodel that into a SolidWorks part that can be manufactured. And you can see we start off with our TruForm results and several of the non-designed components, and then we simply work our way through the assembly, the results, to generate our completed part, which you see on the right. Now, what was an interesting step which MTC, with their experience of additive manufacturing, learned is the part initially developed for function was put through a product called Magix, which identifies where there will need to be support to allow the process of additive manufacturing to create the part, because the part is generated in layers from the base up to the top. If there are many overhanging parts, or overhanging sections in the geometry, then it proves that the part will need additional material. This is what's shown in red to support it during the 3D printing or the additive manufacturing process. So there was a further stage of design and development for additive manufacturing, and one of the key examples is the upper reinforcement section at the top of the part, which you should see with my mouse highlighting, where this was angled, and that angle allows the additive manufacturing process to form that section without the need for additional supports. So that additional process was added in and was proved to be quite enlightening in terms of understanding what is achievable in the additive manufacturing process. So on completion of the development of a design, we can compare the results they achieved. So the stresses on the left, you can see, show a factor of safety in the stress of just over 1 for the baseline design, and then the optimized component has a factor of safety of 1.3, so an improvement in the overall strength of the part. And the stiffness is exactly the same. There's no reduction in stiffness at all, even though there's quite a significant weight reduction. So just to summarize again, here's the comparison of the two parts. You can see quite different in their concept, but fundamentally I think the load paths we can understand from the before to the after, but you can see some of the extra fidelity in the results that TruForm presents and allows the part to be that much more efficient and save on the mass. And whilst this example is developed for additive manufacturing, I think it's reasonable to say that without too much further engineering, the TruForm result could be developed as a machined or a cast component with only a small number of compromises to its design. Okay, so that draws me to an end in overviewing TruForm SW as a product. I think we're looking hopefully reasonably good on timings there at about 40 minutes. Just to recap on some points, that TruForm is available with a discount at the moment, which when combined with the SolidWorks Premium and Basic really does prove to be quite a good offer to get Premium plus TruForm for less than Premium. So thanks to SolidWorks as well for that offer. And if you're looking to understand more about optimization and the methods and tools available, we've got further webinars in December and January for our ANSYS optimization and the latest features of Genesis. So with that, I'll draw the webinar to an end. I'll just wait a few moments. If there are any questions, by all means add them into the questions panel of the webinar. Alternatively, you can contact me at my email address, which I will post to all of you now. Okay, so that's available to all of you should you have any questions following on from this meeting. Okay, I should just give it another minute or so just to wait for any more presentation, any more questions. Okay, I've got one question that's come through. Does TruForm always work in grams? No, the interface is developed so it detects the units you're working on in your model. So if you're working in pounds and ounces, it'll work in those units as well. That's something that's handled internally inside both SolidWorks and TruForm itself. Okay, got another question there. So in terms of how long does it take to run the optimization? So depending on the refinement level that you're working on, the coarsest optimization level will solve in about 1 minute. Standard is about 5 minutes, and the highest refinement, which is what was used for the motorcycle bracket, that solves in around about 45 minutes to 1 hour to present your answer. Okay, good. And I have one more question here. Can you optimize in assemblies? Currently, I think technically it will let you try, but I think it's not something that works as it should at the moment. So I'd recommend optimizing with a part for your components. If you're not aware, you can save an assembly as a single part in SolidWorks. And so if you're having any issues optimizing an assembly, save it as a part, remembering to check the option to save all components into that part. And that will allow you then to perform the optimization on a sort of a multi-body assembly. Okay, so what is the minimum simulation license required? Okay, so the minimum license required for TruForm to work is the standard simulation that's available in SolidWorks Premium. So, okay. Okay, how long has it been a product? So TruForm SW was first launched in January 2014, and our latest release has been available since September of this year. Okay, and just to confirm, GRM, we are certified solution partners to SolidWorks, and we're now working towards our gold solution partner status. Okay. Wonderful. Well, that's good to get some good feedback as well. I hope that you have found the webinar of interest. So if anybody would like any more information, by all means contact me. The tool is available to evaluate for 30 days at no cost. So simply get in touch via our website and we will make it available to you the solution. I see one more question. Is TruForm sold via the VAR channels or direct? Currently it's sold directly from us. However, that's something we want to develop over the next year or so by building relationships with the SolidWorks VAR channels. So if anybody's interested in doing that, get in touch and we would be very happy to talk. Okay, wonderful. I'll just give it another 30 seconds so if there's any more questions. Other than that, I will draw a close to this webinar. Okay, that sounds like everybody is all done. Thank you all very much again for attending. I hope it's been interesting and all the very best for the rest of your days. Thank you. Bye-bye now.